Sure, you can start now.
Okay. So, good afternoon, everyone. Today's presentation title is Building Modeling for Zero Carbon Buildings. And my name is Shediatia. I thank a lot Dr. Zhaoli Zhang for the introduction and for this invitation. I am glad to share with you my research work and my activities that I'm working on during the last year. So as you can see, this picture is the classical construction today for new housing in Europe, most of the time Western European countries. And as you can see, there are some important features that we can recognize from these buildings. Most of the buildings are made of timber. There is building integrated solar thermal systems and building integrated solar electric systems like the PV. You can see also there is heat pumps. The heat pumps are used to heat the buildings. The buildings are very highly insulated, so very good insulated. And here we are talking about a building in the latitude of 54. Latitude 54 is a very high latitude in general. It's compared to the north of China or north cities of China. So you can see here that it is a cold climate and it is heating dominated, and the reflection or the design is not only taking care of reducing the operational emissions associated with heating, lighting, ventilation, but also reducing the embodied emissions. So I want to start by acknowledging Southwest Jiao Tong University. I think it is one of the best universities in China, and I'm working with Southwest Jiao Tong University since a couple of years. I'm very glad for this invitation, and again, I want to thank Dr. Zhaoli Zhang for this invitation for the summer school. And I would like to share with you that the presentation and my work is part of a global initiative on sustainability in the built environment. And you can see that we are trying with a big number of industry experts and scientists and different other stakeholders like organizations and governments to create a consensus on sustainability in the built environment and how to turn the built environment to be sustainable. So allow me to take you now to the presentation and share with you some basic information so that you can understand why I want to share with you some methods or the techniques that are the latest methods and the framework we are using to model the greenhouse gas emissions of buildings. So the first step here is to look at the causes of the climate change, and it's important to look at the causes of climate change. I think we all witnessed in the last 10 years some disruptions, some extreme events related to the climate breakdown, whether they are fires, droughts, heat waves, floodings, and other consequences that are either man-made or nature or reflection of the climate change. And you can see the degradation of nature. So we are all familiar with that. And I remember last year I was in Beijing in September, and there were floodings in the north of China, for example, and the heat waves some years before. So we are all familiar with that, and we can understand that something is happening and going wrong with climate. And if we quantify it from a scientific point of view, we can say that we already reached the 1 degree or the +1 degree Celsius in 2015, and most probably also we already hit the 1.5 degrees Celsius maybe this year, if I am not mistaken. And this means that it's not only 1 degree that has been increasing, but we are talking here about the average. And average means that in some areas, the temperature not only on the mainland, the problem also is in the oceans, because when the ocean's temperature increase, then this means that the whole ecosystem or the whole aquatic system and the organisms are affected, and the whole chain of ecosystems are going to be disrupted and damaged. You can see the phenomena like cyclones and the intensive typhoons and tsunamis, and you can see it in China on the east coast of China. So the global climate change temperature is already exceeded or reached the 1.5 degrees Celsius. And what we are trying to do based on the Paris Agreement, that we try to keep the emissions under the 2 degree Celsius, because we want to reduce the emission on the global level so that the temperature does not reach the +2, because +2 is very dangerous also. +2 means that we will have ranges of temperature exceedance up to 15 degrees Celsius. Imagine your city or your town or Chengdu that the degrees become 15 degrees Celsius higher. This is very, very negative, and it will have very negative consequences. So we are trying to keep the temperature under the 2 degrees Celsius based on the Paris Agreement, which means that all countries must reduce the emissions to keep the temperature. In Europe, it's very dangerous because if the temperature average increased to 2 Celsius, one of the main consequences will be that whole Africa, Central Africa, will have less rain, and there will be a lot of droughts, and a lot of Africans will migrate automatically to Europe. And this can create a lot of problems and political tensions next to the human complexity. Now, what are the causes of climate change? We, in the last 200 years, or let's say 150 years, we burned so much fossil fuel like coal and petrol or fossil fuels in general, including gases, resulting that we altered and changed the atmosphere, and we increased or injected too much CO2 in the atmosphere. And as you can see, these are the normal conditions of the Earth. If we do not have climate change phenomena, the sun will be reflected, the light of the sun will be reflected, and then, as you know, the sun is emitting visible light and infrared light. The visible light gets reflected, and also the infrared light gets normally reflected if we had no a layer of greenhouse gas emissions. But what happened in the last 150 years, that through industrialization and modernization, we went very fast, burning a lot of fossil fuel. And by burning the fossil fuel, we created a layer, this green layer. This green layer is a certain mix of gases, and this mix of gases is trapping or blocking the reflectivity of the infrared, meaning that there is a part of these infrared radiations are absorbed in the atmosphere and re-emitted and re-emitted, and this means that we are in a vicious cycle, meaning that we are increasing artificially the temperature of the atmosphere around the planet. So this is actually the main problem. And when we look at the mix of gases, it's a cocktail of gases that is forming this atmosphere layer that is blocking the infrared reflection. We can find a series of different gases. The most abundant is the N2, the nitrogen, for example, oxygen, and you can see the percentage, it's 78%, 21%, and then you will find several other like water and humidity gases, CO2, methane, nitrogen oxide, all these, and the chlorofluorocarbons, ozone-3, chlorofluorocarbon, hydrochlorofluorocarbon, and so on. All these gases, they are present in the atmosphere, but with a very low concentration. The percentage is very little, very little. Now, don't underestimate these gases, because even a very little presence of these gases can have a very negative effect on the atmosphere, and it will lead that ability to reflect the infrared gets very low. And this means that we absorb the heat in the atmosphere layer that is bordering the Earth. Now, what is the relation between this and what we are working as designers and engineers and building professionals you are all going to work in the mechanical engineering field or in the renewable energy field. In general, you work in the domains of energy and buildings. And this means that you will always need to introduce cooling systems. And you can see in a hot day like today, I don't know what's the temperature in Chengdu. I can check my smartphone. I think the temperature today in Chengdu is now the temperature is 32. So most probably, if you are in a classroom or in a space with many people, you will need cooling. And here comes the question, how are you going to cool? You will need refrigerants. And these refrigerants, most of the time, even though the chlorofluorocarbon is banned, but you can see that we are using hydrochlorofluorocarbon and other refrigerant gases, and these gases has a very negative effect and toxicity on the atmosphere. So it's very important to understand that these molecules or these composition of elements, they are concentrated in the atmosphere, and through the building activities like for heating, cooling, ventilation, electrification in general, for lighting and other purposes, we are resulting in the emissions of these gases. Now, when we look at the causes of climate change, actually what's happening is that with the increased heat and with the reflected infrared radiation, what happens, we are forcing the oxygen to bind with carbon because we are emitting a lot of carbon, and this carbon is resulting into a bending, and this bending creates a new compound, which is the CO2, for example, the carbon dioxide, and also we are resulting this heat, all this radiation, if you can see these lines, they are forcing the carbon to connect with hydrogen, and this creates our big problem of methane. So under the increasing temperature and increasing emission of these gases, we result of having new bonds of molecules, and these molecules, they stay in the atmosphere very long before they degrade. They don't degrade easily, they stay long, and this is meaning that they will trap heat inside them. So this mix of gases is the dangerous part, and as you can see, the most dangerous mixes of gases is the carbon dioxide, the methane, CH4, the N2O or the nitrogen oxide, and all the chlorofluoro, hydrochlorofluoro, or the fluorochlorocarbons in general that are causing huge problems, and they have high concentration in the atmosphere, resulting in the change of temperature. You can see in 1750, we had, these were the values of these numbers. And when you look at 2014, meaning 10 years ago, there is almost the CO2 1/3 increase. Here it's double the methane concentration, the nitrogen oxide increased, let's say, by 10%, 25%, 10 to 20. And then, even though these chlorofluorocarbon are very little numbers, don't underestimate them, because this is the cause of the climate change. So coming back to our graph, it's very important to remember that by releasing the gases that are toxic gases, mainly the methane, the nitrogen oxide, the carbon oxide, which are results of burning fuel or the results of using refrigerants, we are creating a layer of a hot layer surrounding the climate or the planet, and this layer has a mix of gases, and we call these gases the greenhouse gases, which are resulting in heating the atmosphere layer and reducing the release or the reflection of the infrared, and as a consequence, temperature are getting higher and higher. Now, we in the building industry, we use a very famous indicator, which is the GWP. GWP stands for global warming potential. We want to quantify the effect of the greenhouse gas emissions, this cocktail of gases, and we want to do it in a scientific way. So we use a global indicator, which is called the global warming potential. And when we look at these climate change indicators, at the beginning, we were thinking that the whole problem is with CO2 or with carbon dioxide. But in reality, we discovered that one of the biggest problems of the emission mix or of the global warming potential is the methane, and which is 25% more dangerous than CO2 or carbon dioxide. And what is more dangerous is the nitrous oxide. So you can see how the order or the weighing of these different gases, meaning that nitrogen and the nitrous oxide is so dangerous, we have to stop as much as possible any activities of burning, like coal, for example. Coal emits a lot of nitrous oxide, for example. CH4 or the methane is related to cows and mainly animals. And you can see here that eating beef is a very has a very negative influence, especially if we are raising a large-scale cattle with high concentration. So eating beef in itself, it's not a problem, but if we eat it with high concentration and if we use it with abundance, then we will have problems, and then we concentrate the methane in the atmosphere. The CO2, the cause of the CO2 is mainly when we are using electricity that is coming from a power station, for example, that is using natural gas or that is using fuel like diesel. So all the non-renewable sources of heating and cooling, ventilation, and electrification. Now, it's very important to understand this equation for the global warming potential indicator. And actually, this is the equation that we use to quantify the global warming potential when we do modeling activities. And as you can see here, we are mainly focusing on the specific radiative forcing per unit mass. So we try to quantify these gases as a unit mass in kilogram. And when we calculate it, we estimate how much is the weight of the gas and what is the radiative forcing. And we start to do it for the CO2, we are doing it for the methane, and we are doing it also for the nitrous oxide. And then we divide it all by the decay pattern of the greenhouse gas emissions in the atmosphere. So it's very important to understand that there is a decay. I just give you here a graph. You can see here that on a 300 year period, the methane in orange, you can see my mouse or my cursor is following, it can decay and it totally disappeared from the atmosphere layer after almost 50 years. So reaching 50 years after the release of the methane, we can say that it has a negligible presence in the atmosphere. However, the problem is mainly with CO2, because you can see there is a decay of CO2 presence. The composition, if you remember, I was talking with you about this chemical bonding. Actually, what happens over time with the methane, the chemical bonding here gets broken, and then the methane does not anymore exist after 50 years. So this is very good news. But the CO2, the bond between the oxygen and the carbon is very strong bond. And this very strong bond has a big problem. It means that it will take long time before decaying. And you can see after 50 years, we will find only half of the gases of CO2 still existing. And we will have a permanent presence after 300 years up to 1/3 or 35% or 38% of the CO2. And then when we look at the nitrous oxide, it decays a bit faster than the carbon dioxide, but still not so fast, because after 50 years, we still have 65% of this gas connection is still in the present. And then for 300 years, we might have 10% of the gas. So it's very important to understand that normally when we calculate the equation of greenhouse emissions and the global warming potential, we take into account those three main gases: the CO2, as you can see, the methane, the nitrous oxide, And then we calculate the decay pattern, very important, the decay pattern over a period at least of 100 years. And based on that, we can estimate the global warming potential for burning 1 unit of any fuel. Now, as part of the equations that we need to work on, always we try to look at the coefficient for the calculation. So we have some certain coefficient A0, A1, A2. These coefficients, we use them for fractioning the remaining CO2 in the atmosphere so that we can take into account some long-term estimation. And then you can see this curve. These fractions are for the time factor. And you can see here, for example, T1 or Ti is the perturbation time for the CO2, which is 172 years. This is already a very long period for having decay. And then 18 and a half years for T2, and then T3, 1.1 years. And for example, for methane, it's 12 years, the T, and for nitrous oxide, it's 114 years. So we are trying to calculate what are these values after 100 years. Then we come up with these coefficient for calculation, saying how much will be left of the three gases. And then we take these factors and we execute them in our equation, and we execute them in our detailed gases fraction equation, so that we can estimate, okay, after 100 years, if I burn this gas, or if I burn or I heat or I emit these gases, what will be left from these gases after 100 years in the atmosphere? So this is very important to quantify, and based on that, we can see the impact of the different gases. As a consequences, we are not going to, at the end, report the greenhouse gas emission cocktail as a cocktail. We need to aggregate, create an aggregation, meaning that we merge, we unify these emissions. And what we do with the methane and the nitrous oxide, we bring them together, we will check the quantities in kilogram, and then we will do some conversion factors. We will convert them all into CO2, and then we can communicate one universal number. We say, okay, this mix of gases, this cocktail of gases, results into, for example, 2.42 kilogram of CO2 equivalent. And therefore we say always CO2 equivalent, because actually it's not only the CO2. Actually, we are, instead of communicating every gas individually, we are mixing methane with nitrous oxide and CO2 together and reporting as if it was all CO2. And by that, climate science scientists or climate change scientists who are working in the International Panel of Climate Change, there is a lot of Chinese researchers working in this panel, and they are doing very good work. The Chinese researchers, for example, they tell us, take care, we will use this unit of kilogram CO2 equivalent. Why equivalent? Because actually it's not only the CO2, actually this equivalent includes the methane and the nitrous oxide. So it's very important to take this into account. Now, when we talk about greenhouse gas emissions, we need to distinguish two general terms. We need to understand that the world is very complex, and we are talking to sometimes very basic educated people, or we are talking sometimes to professionals, and sometimes we are talking to scientists. So there is different levels of knowledge, and there are different levels of expertise, and I cannot use the same language with everybody. Here, therefore, when we talk non-scientific language, we talk layman language or professional language, we use the term carbon. But carbon is not a scientific word. The scientific word is greenhouse gas emissions. So greenhouse gases are any gas in the atmosphere which absorbs and re-emits heat, and thereby keeps the planet atmosphere warmer than it otherwise would be. And the main greenhouse gas emissions in the Earth's atmospheres are water vapor, There is no problem with water vapor, but we have a problem with carbon dioxide, methane, nitrous oxide, and ozone. So those are the four main gases that are problematic. And I showed you in the last equations that we calculate the carbon dioxide, the methane, and the nitrous oxide in order to estimate the greenhouse gas emissions. So if you are talking to the media or you are talking to non-specialists or you are talking to normal people, you tell them the problem of carbon. But if you talk to scientists and professionals, you have to say greenhouse gas emissions. So any scientific paper, if you are writing any paper or you will write your master's thesis or you want to do any scientific report, because you are at Jiao Tong University, Southwest Jiao Tong University, I advise you always to use the term greenhouse gas emissions because you are like scientific quality. But if you are talking in the street to the people, normally explaining, then you can say carbon. So as you can see, the global warming potential is a very important indicator, and it indicates the amount of warming a gas causes over a given period of time. And like I told you, over 100 years, if you remember, this is the 100-year period over the period of the release of the gases. This is the zero. This is the moment the gases are released. And then this is their presence on the y-axis, their presence in the atmosphere. It degrades over time, but very slowly. So therefore, we need to estimate the period of time in 100 years. And the global warming potential is an index, a universal index or a universal key performance indicator, with CO2 having the index value of 1. And the global warming potential for all other greenhouse gases is the number of times more warming they cause compared to CO2. For example, 1 kilogram of methane causes 25 times more warming compared to 1 kilogram of CO2. So if I remember here, I was showing you this is 25 times the methane more emitting than the CO2. So it's very dangerous, and the most dangerous is the nitrous oxide. So we need always to understand if we burn a fuel, what are the associated gases and emissions released to make sure that we can better quantify that in kilogram of CO2 equivalent. Now, it's important also to take into account that carbon dioxide is the most common greenhouse gas emitted by human activities in terms of quantities released and the total impact on the global warming. And as a result, the CO2 is sometimes used as the shorthand expression for all greenhouse gases. However, this can confuse, and a more accurate way of collectively referring to the number of greenhouse gas emission gases is to use the term carbon dioxide equivalent or CO2 equivalent. Because when we say CO2, it's considered most important greenhouse gas, but some greenhouse gases assessment or reports only include CO2, and this is not right. So they don't consider the other greenhouse gases, and this can lead to the understatement of the total global warming impact. So greenhouse gas inventories are more complete if we include the term GHG or greenhouse gas emissions, not only CO2 or not only carbon dioxide. Now, let's move finally to the building sector. Why I am talking with you about this information and why I am getting into details of the greenhouse gas emission. Because we are responsible and we will be future designers. All of you are future designers, or you will work with existing buildings. And we need to understand that on the global, on the universal level, almost 40% or 39% of global emissions are related to buildings. So we can see that the building sector is responsible for a lot of emissions worldwide, according to the statistics in 2019. You can see the industry is responsible for 30%, transportation is 22%. Maybe we are trying in the transportation to use more electric transport. We are using electrical vehicles. We are using electrical trains. We are using electrical, let's say, containers or trucks. We are trying to do it. It's not easy. We are also trying to electrify the maritime industry. So what these efforts are done in the transportation sector or the mobility sector, There is similar effort in the industry, and there is similar effort in the building industry. When we look at the building industry, the blue color and the purple or this color here, we will figure out that we have 28% of the emissions of the planet come from operational emissions. Operational emissions means that they are emissions associated with running the building. What does it mean running the building? Look around you and check your building you're in or the room you are in. There is lighting. Lighting needs electricity. Maybe there is a heating system. Maybe there is a cooling system. Maybe you have mechanical ventilation. Maybe you need to ventilate the building. Also, don't forget, you have water. In the whole building, there is water, and the water needs pumps, and you are running the pumps. So these are these are operational emissions associated with heating, cooling, ventilating, electrification, lighting of the building. And then we can move to the second part, which is the embodied emissions. Those are emissions related to the construction and to the material, which means that the materials I'm using in my building, I have HVAC ducts, I have a refrigerant, I have a chiller, I have a cooling coil, I have some ducting, I have some walls, I have some columns, I have some foundation. All these components, all these products, they are requiring energy to produce them. And while we were producing them, there were emissions that were emitted. For example, we had to extract the clinker or the main component for the cement industry, and we had to extract clinker from the quarries, and from the quarries we had to get the chalk. We took the chalk, we process it, we put it in a very high oven temperature, the same with the reinforcement steel or the bar steels. We need a lot of energy to get the iron ore to produce it. And this means that we will have emissions associated with the production of the materials, whether the manufacturing or the extraction, and then the transportation and the mounting on site. So it's important to take this into account. And this brings us to the importance of impact assessment calculations. We need to do impact assessment calculations. And as you can see here, we have 4 main phases. I will show you a 5th phase, but let's say we start first. Sorry, those are 3 phases. Phase A, you can see A1 to A5. Phase B, B1 to B7. Phase C, C to C4. Another I will explain it later. But to give you an idea, the phase A is simply the product phase where we have raw material supply and transport. Then we are now manufacturing these materials on the factory, for example, level. This is the A3 level. So we can say the A1 to A3 means the raw material extraction and supply and transport, and the manufacturing of the products that will be used in the process. And then we can say we have phase A4 to 5, which is the transportation and the installation of the site. When you look in the site and you see the crane, and the cranes are building a tower or constructing a building, creating the core, putting the glazing, the facade, installing the HVAC system, lifting the chiller, very heavy gas-powered chillers. For example, in China, you use a lot of gas-fired chillers, and then you lift the gas chiller and then you put it on the building. These are all transport site A4, A5. And then we move to the use stage. Between A5 and B1, we consider that the building here is commissioned. The building is ready to be occupied. So now we start the service life of the building. And then we can say B1 to B2 is the use and maintenance. B3 and 5 are all activities related to the repair or the refurbishment. During the long life of the building can live 500 years, it can live 600 years, maybe more. And then we move to the last part, which is the operational energy and water, B6 and B7, which is responsible of the emissions, especially B6. Because B6 is the stage where I need cooling, heating, ventilation, electrification, pumps for all the circulation of water in the building. And then once the use and maintenance, the B7 is finished, the stage of use is finished, I can move to the new stage, which is the end of life, which is the deconstruction and demolition, or the waste transportation and processing if we will do some reuse or disposal, put it in landfills. So it's important, while we are having a standardized workflow or timeline for the different stages of the building life, we need to name these stages. When we calculate the greenhouse gas emissions, we must make sure I am calculating the greenhouse gas emissions for which stage. Most of the time, when we do building performance simulation or building simulation, we focus only on phase B6. Because in the past, we were only focusing on B6. But today, we cannot anymore only talk about energy. We must also talk about material. So you can see the word material here. It means that I need to calculate the emissions from stage A to 3 and from A to 4. So this is very important to take into account. This means that if I want to calculate the global warming potential for these different stages for a building, I need to do the calculation for minimum 100 years. And I need to make sure that the cocktail of gases, which is carbon dioxide, the methane, nitrous oxide, are taken into account in all activities related to these different stages or the different modules of the building life cycle. Well, recently in the last year, you can find that there is a big tendency and there is a large shout out and call to use bio-based materials. What are bio-based materials? Use wood, timber, use natural agricultural waste, and use these materials as construction materials. And here, what is the advantage of that is that when we use timber, we can store CO2 in these materials. And it's not only about timber, it can be bamboo. For example, in Chengdu, we see bamboo forests, and then we can collect the bamboo, we can cut it, and we make cross-laminated veneer from it, and this could be used as a construction material. Then we can say there's a lot of CO2 stored because during the life of a tree or any species, it will absorb a lot of CO2. And then when we calculate the embodied carbon or the emissions or the greenhouse gas emissions in the material, we can say that we have a negative value, it's minus. But we need always to not to be naive or to be romantic. We should never think that timber will stay long without being incinerated. Most of the time, the stage B, which is the stage of use and maintenance after the life of the building is finished, in the end of life scenarios, most of the time what happens with timber, something happens with timber that we are not taking care of. We burn the timber. Actually, we keep cascading or downcycling the timber materials or the bio-based materials. And as a consequence, we discover that we are releasing or re-emitting CO2 and carbon monoxide and methane because we burn the timber at the end of the life stage. Now, if we can maintain the timber as long as possible and have a legal warranty that this timber will stay at least 1,000 years, 3,000 years, 5,000 years without being burned, then only then we can take into account the negative emissions and consider that the timber is absorbing the emissions and it's a good storage material. For sure, these are all new topics and the research community is trying to find agreement on it, and there's sufficient standards that are working on these topics. So let's do an exercise. If I was with you in class, I would now maybe ask you to take a pen and start to do some little exercise. And it's a just fictive exercise. I copied this exercise from Professor Hendrik Hoxha in DTU, the Denmark Technical University. And he was saying, okay, let's take this wood construction. I have 10 centimeter wood. This is a wall composition. I have rock wool, 10 centimeter. one cluster of 1 centimeter. I have the quantities of the wood, 10 kilogram, rock wool 2.4 kilogram, the cluster is 8.5 kilogram. And let's see on the other side, the concrete. I have, this is a wood wall, this is a concrete wall. For example, a prefabricated wall with concrete brick or cinder brick. So the will be 10 centimeter and the plaster 1 centimeter. You can see here it is 240 kilogram, the concrete, and the plaster is 8.5 kilogram. Now, exercise is that I will ask you to calculate the greenhouse gas emissions for both walls. I will tell you, please, based on these quantities, calculate the greenhouse gas emissions, and I will ask you to calculate the greenhouse gas emissions during all these stages that you can see here, A1 to A3, A4, C2, C3, C3, and C4. So what you will do actually, or in this exercise, you will take this information, maybe you make an Excel sheet or a spreadsheet, or even calculate it manually, and you start to say, okay, I have, for example, 240 kilogram of concrete. What are the emission of concrete per kilogram? Here is the unit, 002 CO2, how much methane, how much carbon monoxide, how much nitrous oxide. And you start to multiply the quantity here with this amount of concrete, and then you start to say, here you go, I have this different gases mixes for the concrete, and then you do the same for the plaster, and you continue the exercise for all the different stages. Finally, you come up with final numbers, and you do the same exercise for the timber wall construction, and then you quantify, and then you say at the end, look at these numbers now, we have these values, and then you can say, finally, this wood composition or this wall has how much greenhouse gas emissions embedded in them, and the concrete wall has X greenhouse gas emission embedded in them. And the functional unit that you must use for both calculation is CO2 equivalent, or CO2 kilogram CO2 equivalent of materials for wood composition and for concrete. And based on that, we can start now to inform the decision making, and we use these scientific based calculations to say which wall composition has a lower or a less or a more less negative impact environmentally on the construction. So I will leave this exercise. You can work on it, and you can do it as a little exercise as part of your summer school and use it. And we can do, if you want to change this exercise and replace it with a HVAC equipment, for example, we can do the exercise for photovoltaic and PVT system, or photovoltaic versus a solar thermal system, or we can do it with gas-fired chiller versus an electric fired chiller, for example. And then we can use the environmental modeling, and we can use our mathematical equation here to estimate the global warming potential for different building products, for different building components, for different building systems. Based on that, we try to choose low carbon solutions so that we can reduce the embodied emissions, and we reduce also the operational emissions. So this was the first part of today's lecture. I wanted to create a basic foundation about the calculation of greenhouse gas emissions and the causes of climate change, and how can we, in a concrete way or a specific way, come up with the calculation. Now allow me to continue with the next part of today's presentation, which is the carbon neutral community. Now, if we agree that we want to have low carbon or low greenhouse gas emission communities, meaning that we must not only focus about reduction, but we want to have neutral, carbon neutral communities as much as possible. Because we want to reverse the heating phenomena of the planet. The planet was heated in more than 200 years or 150 years. It got very hot. Now to turn the planet, cool it down back, it will take many, many years. Not before 300, 500, or even maybe 1,000 years before we can cool down the planet. So to make sure that this atmosphere is cooling down, we need to stop releasing the greenhouse gas emission gases and make sure that we are building carbon neutral communities. So as you can see, the whole world is quantifying every while the emissions, and you can see worldwide we are trying in Europe, these are the EU 27 countries, to reduce the emissions. We have an objective in Europe to reach the zero carbon continent by 2050. China has the same target. China wants to be also a carbon neutral continent, sorry, not carbon neutral country. And China is going to do it maybe not in 2050, but in 2060. So if you see the national plan for greenhouse gas emission of China, China wants to be carbon neutral by 2060. So maybe 10 years after Europe. I am not sure if Europe will make it on time. I have a feeling that China, even though it has longer term objective and it will reach the 2060, I have a feeling that China will beat Europe and will become earlier carbon neutral when we look at the numbers and we look at the speed of installation of renewables in China and the production of them. So you can see here that in the 90s, for example, Europe had all the time increasing emissions from the power industry, the industrial combustion, building sector was almost stable, the transport was increasing, other sectors increasing. And when we compare what happened in the 90s to the 2021, maybe you can say, yes, there was COVID, but still, in general, there is a trend to go lower and lower and lower. Now, as you can see, unfortunately, Europe is going higher in transport, and you can see that Europe is very slow with the electrification and reduction of emissions of its mobility sector. Unfortunately, the European Union is not allowing Chinese cars to get in, and they just added last week 40% tax, additional to a 10% tax, meaning that if I want to buy a Chinese car in Europe, I have to pay 50% more of its original price. But these practices will only delay the Europeans' reduction of the mobility sector because today Europe is not producing enough cheap or let's say affordable electrical vehicles, resulting that the whole mobility sector is still on the high regarding its emissions. So it's very important to understand that the building sector, your use of transport, your heating, your cooling, your electricity need to be neutral, carbon neutral in the coming years. And therefore comes the concept of zero carbon buildings. And as you can see, a zero carbon building is a grid connected carbon efficient building that balances its total annual carbon emissions by on-site generation. And if we look at the basis of design, first of all, we need to apply the bioclimatic design principles, which are about passive heating, passive cooling, natural lighting, all these principles that are involved. Then we have to introduce energy efficiency in all appliances and equipment and systems, whether in LED lamps, efficient cooling, efficient heating systems, efficient ventilation system, heat recovery system, and so on. We need also to maintain indoor environmental quality. We need to make sure that we have respected or complied with minimum thermal comfort and air quality and visual quality, visual comfort requirements. And then we can introduce efficient cooling system. And finally, any zero carbon building must have a renewable energy system integrated. So this will be the future houses, how they are looking, or actually we are already building these buildings today in Europe. And when it comes to the embodied carbon, you need to be aware about the following. Let's look first on the graph on the right side. The material's embodied energy content is very high into the reinforced concrete, in the brick, in the clay, concrete, any autoclaved aerated concrete has a high energy content, sand lime brick, cement mortar. So these are all very high energy intensive materials, and as a consequence, they will have high emissions associated with their production. And most of the time, they are produced from non-clean energy sources, meaning either they are produced from gas, natural gas, or from fuel, fossil, or from coal, and these are all negative impacts. While when we look at the down at the wood, straw bale, or hemp, we can see that they have less energy, they are less energy intensive, and as a consequence, they are either have a carbon negativity, which is the capacity to store CO2, which we all want to do, because today carbon storage is the hot topic across the world. And as a consequence, you can see that we are trying to avoid using cement-based construction. You can see here, this is a classical cement-based construction with classical aluminum or PVC windows. We have external wall finishing of mineral plaster. We are using underground structures of reinforced concrete. We are using reinforced concrete in the slabs, in the columns. All that is cement-based technologies. Today, we are moving in a new type of construction, which is timber-based and bamboo-based construction. Therefore, it's very important for future mechanical engineers that they learn better about timber buildings and bamboo buildings, and to understand their properties and their building physics properties and how they behave thermally, so that you can better design and select and size the HVAC systems or the heating, ventilation, and air conditioning systems that correspond to the nature of these buildings. And as you can see today, high carbon buildings or high carbon materials are all like insulated triple glass, wood aluminum window frame, PVC window frame, wood window, waterproof membrane, steel in general. Low carbon should be something like mineral plaster, solid wood, ceramic tiles, bamboo cladding, bamboo flooring, solid wood gypsum, cross-laminated timber, glue-linen timber, OSB, concrete deep foundation, clay plaster, and climate negative, which are the materials that can store the CO2 at least for 100 years or until the building is incinerated or the building is dismantled or demolished, is including solid wood, hardwood structures, CLT, glue-linen buildings or cross-laminated timber buildings, hemp fiber, reed mats, straw. And this is today the trend worldwide, to use these climate negative materials and to create different construction technologies for the building, to have high-rise tall buildings that are made of timber and concrete. For sure, we have a lot of problems with fire. We have a lot of problems with acoustic. Maybe we will end up having hybrid construction, a mix between concrete and timber. But in any case, today, any engineer who is working in the building sector, he or she must calculate the embodied emissions. And as you can see today, we can find a lot of software like available software that can calculate the emissions while you are designing your building in Revit, for example, or you are using MEP Revit, mechanical, electrical, and plumbing systems. You can directly see the impact on the global warming potential, and then you can say, okay, I am exceeding the budget and above the budget. If you are in the green range, okay, this is low kilogram CO2 equivalent. This is very high, and based on that, you can assess your choices. And we can see already that it is not science fiction already. Since 3-4 years, France is requiring a limit of kilogram CO2 equivalent per square meter of constructed buildings in the residential sector, for example, and you must calculate all the materials and greenhouse gas emissions associated with these materials, and to be under a certain limit or a threshold defined by the French state. Same story applies to Denmark, that is having now a limit, I think, of 7 kilogram CO2 equivalent, not anymore 12, it became 7. They just voted 1 month ago in May the values, so you can see that there is now more and more restrictions, not only on the operational emissions, but also on the embodied emissions. This means that the big elephant in China or in Europe is not new construction, but it is existing buildings. And this means that we need to think about solutions. Are we going to renovate the buildings? Now, I know that most of you will say, okay, I live in Sichuan province. It's not a big problem. I don't need to do insulation. But you can see in the cold climate of China, for example, in the severe climate in the Tibet or in Xinjiang or in the northeast in Hubei or in Harbin or all these northern provinces with high mountain or altitude, China will have a very cold climate and we can have cold spells, and it is not acceptable to leave the buildings without insulation. Because if you keep the building not insulated, the buildings will be consuming very much energy for heating, or the people will not be comfortable. So they will be poor and they will not be able to get integrated in a socio-economical system, meaning because of the bad comfort, they cannot be productive, they cannot learn, they cannot study, they will be sick, they will have very restricted activities and functional operation. So here is important that we think about if the building is not insulated, look at the heat demand, the domestic hot water demand, the ventilation demand. All the time the building consumes a lot of energy to make people comfortable. If I am insulating it with an industrial solution, like a fully integrated industrial solution system, for example, as you can see here, this is a project in Austria, and they are insulating massively old buildings with prefabricated solution. We can see that we can reduce the energy, the operational energy, and then we can reduce the operational emissions. As a consequence, if we install or integrate photovoltaics or PVTs, we can also reach a zero carbon neutral balance to this equation. So this is very important to take into account, evaluate these strategies to increase the deep renovation rates in general, to gain money and to save energy, and the most important also, to achieve thermal comfort. As I told you, I'm not going to make these solutions in the south of China. I don't need to do that maybe in Chengdu, but maybe I need to do it in Harbin. So these are examples, or I need to do it in Ormik. I don't know. It is important to think on the Chinese context. We are doing this anyway in Europe in any latitude higher than 50. So what will be then the most common technology for heating and cooling net zero carbon buildings? As you can see here, this is an example of all the technologies that we are using today in these buildings. We are using solar panels, radiators. We are using a lot of hot water storage systems, 2,000-liter storage tanks, 1,500-liter storage tank. We are using underground or underfloor heating systems. And for sure, we have famous heat pumps, but not only classical heat pumps for cooling. We are using reversible, or for heating, we are using reversible heat pumps that can allow for having a water supply, a hot water supply and cold water supply, and they can also meet the requirements for domestic hot water. So the challenge today that all mechanical engineers will be living in the coming future is that they will not anymore use the high temperature systems that are up to 90 degrees or the average temperature systems of 55 or 70 degrees Celsius. Today, we just need 30 degrees Celsius water temperature of my water loop, of my hydronic water loop in the building. And with the 30 Celsius, the building is very good insulated. It is airtight. I don't have a lot of leakages. As a consequence, I can heat it only with 30 Celsius hot water. And for domestic hot water, I will just use 55 Celsius for salmonella or for different, avoiding certain bacteria. And this is easy because then I will have a low or a small container of hot water, for example, 60 liter or 50 liter, or I can use direct electric heating in case I have sufficient photovoltaic and sufficient radiation out of the winter season. You are all familiar with the all-electric heat pump concept. We will have simply a refrigerant. This refrigerant, we will expose it to very high compression, exactly like when you are pumping your bike. You keep pumping the gas, putting it under pressure, under pressure, under pressure. When you put the gas under pressure, the gas releases heat, and this released heat, I use it to couple it to a water loop. And then I have a hot water loop from compressing the refrigerant. Once this cycle has been achieved, I can now move to the expansion valve, reduce the pressure, and allow the gas to expand on the outside unit. In this case, we will have the evaporation, and the heat of this evaporation will be rejected outside my house, and then I can start again the loop and start again with the compressor. So the heat pump is one of the number one or the most successful technologies that will be in the future used in Europe. Today, most European heat pumps, we import them from Japan, from China, from Vietnam, from Asia in general, and Asia is very leading in heat pump production. It will be very important that already China tries to modernize the buildings that are in extreme climates by introducing insulation and air tightness, and in the same time install the photovoltaics and the solar thermal systems and install heat pumps. This will be a very successful situation, especially that many cities in China, they are not only heating dominated or not only cooling dominated, they are mixed. They need heating in the winter, they need cooling in the summer. So as a consequence, if we are looking at the design of a zero carbon building, one of the most important things we have to think about is to diminish the energy losses, use sustainable energy resources, use as much as little as possible fossil fuel, or even avoid if possible, and this will get us to the Trias Energetica principle. This Trias Energetica principle allows us to achieve a very logical design and put a priority. What should I focus on as a designer? And if you want to have a translation of the Trias Energetica, you can look at the right side here of the steps that you need to do as a designer. You need to first reduce the load or reduce the demand for heating and for cooling and for lighting and for ventilation. Then you have to use passive opportunities for natural cooling, natural heating, natural ventilation, natural lighting. Optimize active systems. If you are using any active system like lighting, LED lamps, if you are using heating system, cooling system, all that needs to be optimized. And then number 4, you incorporate renewables. And once you incorporate the renewables, you are ready with minimizing your waste overall. So these are the basic principles of any high performance design or any net zero carbon building design. And here is like what I gave you as an example. This is a project. It was constructed in 2024. They opened it this winter. And as you can see, heat pumps, a lot of solar electric. This is at least 15 square meter of solar electric panels. Efficiency is 18. Most of the panels are coming from China. The solar thermal system is 2 square meter. And we have a heat pump. And the building is insulated with ecological material, finishing is timber, and even the brick on the ground floor is just cosmetic brick. These are not full bricks, these are kind of glued units of brick, just to give the feeling of brick, because in the lowlands or in Belgium and in the Netherlands, we have a connection with brick, so we try to give the feeling so that people don't feel suddenly the transition from classical brick buildings to timber buildings. And for sure, windows are very high performance, and you can see there is a air exchange system, mechanical ventilation, and those buildings are very efficient. The temperature inside for the hot water loop is 30 degrees for heating the floors, and there is for domestic hot water tanks of 1,500 liters. Now, this means that we are in a very big transition worldwide, and we are now in the middle of the transition. We have only 25 years left to achieve the zero carbon targets in China or in Europe. Maybe China, you have 5 years more, we have this. And as you can see, we need to take into account that even the power stations or the energy production stations, they need to be focused on renewable systems, hydropower, as much as possible so that we don't have high emissions associated with energy production. And as you can see, when we calculate the greenhouse gas emissions and the energy use intensity, we always use this classical exercise that we will quantify the emissions associated with lighting, equipment, cooling, pumps and fans, heating, hot water. We divide them by the gross building area, and then we report them. In the past, we were reporting them into energy use intensity. Now we are reporting as carbon use intensity or carbon emission intensity. So this means now we always need to say how much kilogram CO2 equivalent associated with square meter of. On the long term, how will be Europe and how will be China? As you can see, this is the future. We will move from single building concepts to full community concepts. We will look at electric neighborhoods, full electrification. We want to electrify the whole building sector. We want to get rid of fossil fuel, and this means that we will invest a lot in energy parks, nuclear energy, windmills, hydropower, and solar farms, and those will be serving cities. Cities will be full electric, mobility will be full electric, houses will be full electric. With the use of a heat pump or underground district heating or district cooling, we will be able to electrify completely the building sector, and as a consequence, slowly neutralize or clean the energy mix to get out of the energy mix coal, natural gas, and fossil fuel. And don't forget also that China very soon will stop using natural gas for cooking. If you like cooking like me, I like very much cooking. For me, it was a very difficult transition in my life because I was forced to stop using natural gas. I had to sell my stove and I cannot anymore use gas. I only can cook with electricity. And I got an induction stove. And as you know, cooking with electricity is not like cooking with gas. This transition will happen in China sooner or later. It's already happening in Europe slowly, but it will be a very important also on the lifestyle in general. Now, allow me to move to the last part of today's presentation. We have 15 minutes left. And in these 15 minutes, I want to share with you our framework, modeling framework that we are using in the lab to model the carbon, zero carbon building in general. And it's a complex framework because from one side, we need to model the energy use and the emissions during the use of the building life. And we need to in very detail, based on building physics and thermodynamics, to represent the building and the building systems, meaning that we need to represent the building geometry, we need to represent building HVAC systems or heating and ventilation and cooling, we need to represent the different openings, insulation, and at the same time, we need to make an inventory of all materials and check the tables or the databases with the associated emissions. And normally these are done in two separate communities and separate worlds. Today it will be falling on our shoulders responsibility. So allow me to give you a very short introduction about modeling, building modeling. What is building modeling and why is it important? Well, we use building modeling for design decision support. You will be a designer, you will need to make big choices, and you will need to check the influence of certain design options on the carbon emissions, on the energy use, on the HVAC choices you are making, and the sizing of your systems, including the renewable systems, daylighting, natural ventilation, the thermal mass. Also, you need to do cost modeling, and you will need always to model also the design process itself, the workflow. So in this context, we can see here, this is an example of a building in the United States. It's the NREL, the National Renewable Energy Lab, for example. This was a conventional design, just a box. And you can see the idea of having a box building was influenced in the 60s and the 70s that we can use artificial lighting, we can use artificial mechanical ventilation, we can use cooling, and this means that we don't need to design the building in a smart way. But today, since we want as much as possible to not use energy and reduce the use of energy and benefit from the natural climatic phenomena, lighting, air, and so on, we are now trying to use energy modeling to make smart building geometries and smart building design. And as you can see, this is the smart design, the same area on the right. Here it is better distributed spatially, and we can see that the whole roof is covered by photovoltaic. There is more window openings, there's natural ventilation, there's natural lighting. And as a consequence, the whole building consumption is reduced by 80%. 80% energy reduction just for smart design and for checking different design assumptions using building energy modeling. So this brings us to our framework that we are working on. We developed a framework that is just published last month in June. And this framework is called the Framework to Model Building Carbon Emissions. And we have a report, it's open access. You can access it on the link here. And this framework is based on 10 modules. The 10 modules allows you to model the carbon or the greenhouse gas emission of any building in a very systematic way based on international standard. You can apply it in China, you can apply it in Belgium, you can apply it in any country in the world. You can do it for a big building stock, or you can do it for a very specific building. You can do it for a shoebox, hypothetical building, or a rebuilding. So this is the advantage of this system. And the idea here is to help with evaluating the greenhouse gas emission based on scientific methods and standardized techniques. So one of the first modules that you can see here, the framework is made of 10 modules. Module number 1, it asks you about the approach of modeling you want to follow. Then you have to define the climate and the location. Module number 2. Module number 3 is the building characterization. Module number 4 is the building envelope and renovation measures. Module number 5 is the life cycle assessment. Module number 6 is the HVAC systems and electrical and storage systems. Module number 7 is the energy mix and the carbon fractions. Module number 8 is any additional parameters for allowing for any backup scenarios. And module number 9 is the evaluation scenarios and the functional unit that will be reported. And finally, module number 10 is about sensitivity analysis and uncertainty analysis in the context of result interpretation and results post-processing and visualization. So as you can see, module number 1 is called carbon modeling approach. And today there is 2 carbon modeling approaches worldwide. The first one is called the top-down approach. And in this approach, you will be either having a budget of emissions for your building. This we can see it already like happening in France, for example, or happening in Denmark. Before designing the building, there is a rule that tells you you cannot exceed X emissions or a certain amount of greenhouse gas emission or CO2 equivalent kilograms per square meter. And this means that you have a budget. You have X kilogram CO2. Your design should not exceed this budget, regardless of whatever design choices you make. And this means that you have to quantify the embodied greenhouse gas emissions or carbon equivalent carbon, and you need to quantify the equivalent embodied and operational emissions. Option number 2 is more the bottom-up system, which is the classical. It's the other way around. It's mainly when we do simple modeling for an existing building or a building that has no specific requirement to reach certain greenhouse gas emission threshold. And in the first module, we explain the 2 approaches, and you have to choose one of them. I think so far in China, you are most of the time will be using the option 1B, because in China you don't have certain targets. But I hope in my collaboration with future researchers and my collaboration with Professor Jingping Yuan and Professor Dr. Zhao Li Zhang and the whole team of Southwest Jiaotong University is that we start to explore this option of the greenhouse gas emission budget, because it's very exciting and it will be interesting in China. And maybe even if we can bring it to standardization in China, it will be very useful, not only with Southwest Jiaotong University, but other universities in China. Second module, which is very important, you need to define, is you need to select your weather data, and you need to select your climatic region. And here we are referring to a very good standard, which is actually 169. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, and they classify the world into 6 climatic zones covering all countries of the world, and they allow you to find any city and have a classification based on the cooling degree days and the heating degree days in a very scientific way. So all you need to do in this sense is to define what are the climatic zones that you are falling in, and you need just to define, are you in the city or out of the city, to include or exclude urban heat island effect. And then you can select any city in these cities around here. I don't know if we have Chinese cities here. Maybe we have, I don't see, this is Sao Paulo, Cairo, Barcelona, Busan, Tehran, Santiago. I don't see Xi'an. I see Xi'an. Xi'an is in 4B, for example. But for sure, you can select any other Chinese city in the region of China here, as you can see, and make sure that it is falling in a certain climatic. Here we try to use these cities for cross-comparative studies. So let's say if you want to make an international study worldwide and compare, but for sure, I think China, most of the Chinese cities will be falling between category 1A until south of China will be maybe up to maximum, maybe will be in the category of 1, 2, 3. Maybe also something about 6 because of the north of China. But anyway, these are all examples to be chosen, and based on that, we can move on. And we advise here is to use certain weather databases like Meteonorm, or if you have a national weather data file, this will be very good. We advise to use historical data and future data, and then you can do predictions. And this is an example of a study that we were using future weather files in order to estimate the emissions and the energy use in buildings. Module number 3 goes further into detail, talking more about the building characterization. And here you need to define what is your building type. Again, I refer to ASHRAE 169, which is a very good standard because it allows you to have high performance building requirements for all climatic zones in the building. So even if you are not from China, let's say you are from a country that has no building standard, you just need to define your climatic zone, like we said here. And based on this standard here, this ASHRAE 189 for the design of high performance building, you can find tables that are telling you what are the best window to wall ratio for your envelope, what are the best efficiency for your system, what is the best U value for your envelope, what is the best air tightness. And you can start to define whether you are going to use a shoebox, theoretical shoebox, are you going to use a real building, or are you going to model a whole building stock for a city, for a town, for a neighborhood? So these are all available options how to represent the building in the framework. And then you need to define the structures and finishes, and finally the material quantities for your choices of material. So this is, for example, as an example, we selected here a shoebox. It's a best test ASHRAE test. And we take this shoebox and we start to say, we will start to model this shoebox, and we will do it in Brussels, and we will start to use the dimension for our model. We will use a single zone, and we will just have one single orientation. The worst orientation will be south, for example, or southwest. And we can proceed with that. As part of module number 3, where you are doing your building characterization, you will need also to define what type of structure are you using, lightweight, heavyweight. For example, lightweight if you are using a timber structure, if you are using a concrete, it will be heavyweight. What is the material finishes? And then you need to define your list of materials like plaster board, glass wool, structural timber, and so on, and translate material into quantities. So it's very important to start your inventory early, and then you can be able to move to the next step, is to define the building physics characteristic of your envelope. Like I told you, you just need to define if your building envelope is poor, low energy, or ultra low energy. If it's poor, it means that the building is not insulated. Then you can check certain properties, common properties found in the reality of your context where you live. If it's a low energy, you can also refer to your context, and if it is ultra low, you can use the standard 169 of ASHRAE. Once you are done with module 4, you move to module number 5. And in module number 5, all you need to do is to define your different stages of carbon calculations. Are you going to calculate module A1 to 3, A4, 5, like we talked earlier? Are you going to include A1 and from A1 to A5 and B6, especially that B6 we said it's the most important for operational emissions, and if you are going to take into account the end of life or not. So it's very important to take this into account and calculate these different emissions. And we mentioned earlier is that when we do a life cycle assessment, we try to quantify the impact during the fabrication of the material, during the utilization, and during the elimination. And based on that, we can compare product 1 with product 2 with product 3. And this is here an example. For example, if somebody comes and tells me, I want to use acrylic dispersion paint, I want to color or paint my room, shall I use acrylic dispersion paint, or shall I use natural dispersion paint, or shall I just use lime wall paint? What I'm going to tell you is to do a life cycle assessment, and every time calculate the energy in kilowatt hour or the emissions in greenhouse gas emissions associated with painting 1 square meter of the wall paint. And every time I tell you quantify. And as you can see, acrylic dispersion, it is consuming or using 1055 kilowatt hour for 1 square meter of paint. Natural dispersion paint is using 177 kilowatt hour for 1 square meter or 100 square meter, and the lime wall is only using 18 kilowatt hour for 100 square meter of paint. As a consequence, it's very easy. If I want to have a low greenhouse gas emission or low carbon equivalent paint, I will use the lime paint. So this is how we can use this example to apply here in this calculation. For sure, you will need to have some end-of-life scenarios also for your building. You need to tell me how long, especially for the phase C. Is this building going to live 500 years, 1,000 years, 100 years? What happens after the 1,000 years? What happens after the end of the life? Is it going to be demolished? Are you getting dynamite and exploding it like we see in a lot of American movies? Are you going to dismantle it? Are you prepared, or did you prepare the building to be dismantled? This is all part of the equation, and based on observations, then we can apply the ISO standards or the European EN 15798 or the EN 15804, which are all standards that allows you to report in detail the emissions from the mining stage of the material to the transportation, to the manufacturing, to the construction site, to the usage stage till the end of the life. And like I told you, why we have a problem of timber? Because most of the time we are incinerating timber and we are not reusing timber. Either we incinerate timber or we landfill it, resulting that the CO2 is again released in the atmosphere. And we all know that if we want to save the climate or the planet, or we want to reduce the global warming of the atmosphere, we need to store the CO2 for 1,000, 3,000, 10,000 years. So it's very important to think with a very long-term version. Here are the life cycle stages we talked about before. It can be part of your module. And finally, here you can move on with your stage and define the stages of your calculation. Unfortunately, when we do embodied greenhouse gas emission according to the European Standard 15804, we have to only calculate the greenhouse gas emissions for 50 years. And we can take the life stages A, B, C, and we use, in our case, for example, a database like Econvent, We do not recommend to use environmental product declarations, whether they are generic or specific, because they are made by third party, they are made by the industry, so the reliability is not high. It's better to use reliable databases. And when it comes to HVAC systems, also we need to quantify all the ducts, all the systems or the equipment, the machines, the heater, the boilers, and so on, the gas boilers, the chillers, and so on. And we can use, for example, temporary one-click LCA, MEP, or just mathematical equations to multiply the amount of quantities of materials for our HVAC system, including the ducting and so on, by the emissions expected. And if we have any bio-based material, we can calculate the biogenic carbon model -1 + 1 calculation, assuming that the emissions or the bio-based materials will be incinerated or landfilled after the end of life of material until so far. And for the database types that we can use process data or hybrid data or input-output data, depending on installation. Here, for example, we have access to the EPIC database that we are working on, but this is just an example. When it comes to the HVAC, electrical, and storage systems in Module 6, you'll need to look at your choices. If you have a basic building, does it have mechanical ventilation? Yes or no. Is it heated? Is it cooled? Yes or no. If you have a low efficiency building, then you need to maybe assume that you have a gas boiler or air conditioning system. Maybe you have mechanical ventilation, you don't have mechanical ventilation. And if it's an ultra low energy building, most probably you will have a heat pump coupled to mechanical ventilation or not. PV, PVT, solar collectors, you have district heating or district cooling, you have a geothermal network in general or a neutral network in general, and all the options related to storage, whether you have water tanks, whether you have phase change materials, whether you have fuel cells or specific batteries, all that can be reported from a building physics point of view in regard to the CO2 coefficient of performance of your heating system or cooling system, your fuel type, ventilation, mechanical ventilation presence, yes or no, and the photovoltaic efficiency and surface. This brings us to the module 6, and based on that, we can integrate these aspects and calculate the emissions related to the use and to the embodied emissions. And in this example here, we can also define the energy mix and the carbon scenarios. We can do current calculation based on historical data. For example, China today has a dominated energy mix. Maybe in the next 10 years, it will be dominated by renewables or by hydropower or by nuclear power. We never know. So it's allowing me this framework to use the current energy mix emissions, but also add future scenarios depending on your context. And then we can move to the module number 8, which is the additional parameter. If you want to add a carbon tax, if you want to have a certain threshold of emissions, like I told you before, we have in Europe a carbon tax. Most probably by 2028, it will be obligatory in the residential sector. So if you emit more than a certain amount of CO2 equivalent, you will pay a tax for every ton of CO2. So these are type of examples that could be added to the framework. And then finally, the framework moves to the final reporting part, which is the evaluation scenarios and functional unit. And here we are talking about a reporting of the operational energy in kilowatt hours per square meter per year, and the reporting of the greenhouse gas emissions for the embodied and the operational emissions in kilogram CO2 equivalent per square meter per year, and finally cost in euro square meter or in yuan or RMB in per square meter, so that you are reporting this universal data, and then your building can be compared how far it is low carbon, zero carbon, or not. These are just examples of some simulations we conducted. For the operational energy, for example, we have an existing building, and then we introduce some improvement, renovation solutions. Now the emissions are reduced. We have PV generation, and we have PV heating, and we have electricity use. And you can see every time we introduce a scenario, we are trying to reduce the emission on the long term. And here we are comparing the net primary energy in general for always the base case and for the renovation scenario. So these are always examples in the current situation by 2050, by end of the century. And here we are using primary energy factors based on the European Commission database that electricity has a factor of 2.5 and natural gas has a 1. Other example of calculating the greenhouse gas emissions embodied and operational, same story, base case against the new renovated building. And every time here we are operating both emissions and the energy emission factors for both cases, taking into account all the materials of the calculation. And this is also another example where we are having the operational emissions and we have the embodied emissions for the different scenarios. As you can see, once we add a lot of materials, the embodied emissions increase, especially if we are using traditional materials and non-low carbon emission materials. Last step of the module is to do the sensitivity analysis, which is very important in any modeling work, and the uncertainty analysis, maybe some hot spotting visualizations, and finally the post-processing. And this is simply the conclusion, the final conclusion. You can see that this is the framework. We were thinking in every detail and every step. We designed the 10 modules, and in every step, whether it's the electrical system, whether the choice of the heating system, the cooling system, the installation of renewables, the choice of material for the envelope, the choice of material for the structure. At every stage, we are able through this framework to calculate the operational emissions or the operational energy over a period of 50 years or 60 years. And we are also able to calculate the embodied emissions. And every time we can report this information. So what is very important from the beginning is to have a very good life cycle assessment database of your materials. It's very important to identify the greenhouse gas emissions targets that you want to reach. And it's very important to explore different decarbonization pathways and to use universal key performance indicators and check if you will have violation values or severity values of emissions so that you are able to calculate the greenhouse gas emissions with from a comparative approach, allowing for alternative development rather than going for an absolute design or a single design. Because there is nothing called the ultra optimal design. We are always looking to a wide solution space for nearly optimal design solutions that are all reaching the nearly zero carbon objective, or they are already net zero carbon. By that, I end today's presentation. I am open for the Q&A session and today's presentation. Thank you very much for your attention. Thank you.
Okay, thanks for your excellent presentation, Dr. Sheldon and Tia. And anyone who have a question?
Oh, teacher, I have a question.
Yes.
Can you hear me? Yes, Professor. I think according to your class, I think the Xinjiang province is suitable for your medal. So I don't think the medal is suitable your like my city. I'm located in the Chengdu. You know, there is many people, so we have to build the high buildings, and I don't think there is no land to build the mode. But I think even in the Xinjiang province, I think their economic is very low and their education also low. So there is no, I think there is a little of a person want to build these buildings. But I think if the world can solve the of energy, I think the model will be very useful. And I think it will be used in the big cities, you know, like the high buildings. Yes, that's all my ideal.
Thank you for your question. I understand your concern, and I agree with you. The big challenge in China is high rise, and we need to take care of that aspect. That it will be difficult to do tall timber buildings or high rise timber buildings. It will be very difficult because we will have problems with fire. We'll have problems with acoustics, safety, and we have one of the largest timber towers in Norway. It's 12 floors, I think, and still many cities are afraid of tall timber buildings. But I believe that China will not build low rise. China will continue building high rise because you have scarcity of materials. And I fully agree that we should go for high rise buildings. But what we will going to do in the next year in China is that we will have more systems that are using low carbon materials. For example, low carbon concrete. We can go for concrete that has biochar. We can try to have concrete with lower emissions. We can try to have concrete buildings or steel constructions that are using fiberglass or using smart bio-based fibers. So we keep the high rise. I agree that high rise has to be priority in China, but we try to use materials that are less energy intensive. So this is for sure. Plus, I think in the future, the photovoltaic technologies and the solar thermal technology will be more and more cheaper, that we will use them as cladding. So even in a high-rise building, we can use the facade surfaces and the roof for photovoltaic cladding and solar thermal systems clad. So I think there will be a lot of evolution. Maybe China will not be 100% net zero carbon buildings, but nearly zero carbon buildings. And this means that we keep the high rise, that we change the use of material, and we integrate more renewables and use more efficient heating systems. The other thing about China, when you say in some regions economically they are still not developing, we should not forget that China eradicated poverty of more than 900 million persons in the last 10 years. So one of the Chinese miracles is that you are able to eradicate poverty. So if China will continue economically to progress, more people will have ability to get out of the social class and move to the middle class. And more people will move, increasing the middle class, we can create a demand. So I agree, maybe now in the province or your region, economically, it is not feasible, but don't think that it will stay like this for a long time. Very soon, many people or many communities will move from the social class to the middle class, and this means that they can afford better buildings qualities, and buildings will have a more zero carbon output. Thank you. Other questions?
Any question? Anyone want to ask question about zero energy carbon building or something like that? Okay, I think no one will ask a question. So, thanks, Sheldon and Atia. Thanks for your excellent presentation. We have learned a lot about zero energy building, like function, like its function, is how to construction zero energy building and how to evaluate zero energy buildings. Thanks very much. And I think that's all for today's class. Thanks for your
Thank you very
attention.
much. Good luck with your summer school. Yeah.
Okay.
You are welcome.
Okay. Thank you.
Have a good day.
Okay. Okay.
Thank you for the
Okay.
invitation.
That's all for today. See you.
Bye.